Welcome to ECE 302. This is lecture 2.3 on Axioms of Probability. I am Professor Stanley Chan. Here's the outline for today's lecture. Last time we have talked about probability space, where we introduced the three elements of a probability space, which contains the sample space, the event space, and also the probability law. In this lecture, we're going to discuss three axioms that defines the probability law. And then we're going to look at a few corollaries that will be derived from the axioms, and then we will look at some examples. Let's recall what is a probability law. The probability law, it is a mapping from the event to number. And so the probability law is a function P that takes elements inside this event space. Basically, they are the subsets of the sample space. Okay, so this is called the event space. In other words, you're taking an event and then you're mapping to a number between 0 and 1. Okay, that maps an event to a real number between 0 and 1. This function, that's called the probability law, this P, must satisfy three axioms known as the probability axioms. Now, as you can recall, what we really want the probability law to look like, well, there are a couple of things we want. One is that if you apply the probability to something that's empty, you don't want it to be 0, okay? And if you apply the probability to 1, it has to be 1. And then if you recall, we have example of getting ahead. If you have 1/3 here, then the probability of getting a tail, it should be 2/3. Right? So we argue that this set of assignments makes a lot of sense in real situations. And so you can see what these three axioms are about. The axiom 1 says that non-negativity. So basically, for any element A, this probability has to be bigger than 0. Okay, for any element A inside this curled F. So it should make sense to you, because if you put an event A here, and if the probability law gives you a negative number, it doesn't have any physical meaning. Okay, so you really want the probability to be bigger than or equals to 0. And then the other axiom says that the probability of the entire sample space is 1. Okay, so that is what we want. Okay, if you put the entire sample space and the probability is bigger than 1, that is also not right. Okay, can you have why are you setting it to be 1? Why not setting it to be 10 or 100? That's just for convenience. Okay, so as long as we're consistent with this definition, we are good. Okay, so you have non-negativity, you have normalization. And then the third axiom is called the probability law. Okay, it's called the additivity criteria. It says that for any disjoint subsets A1 through A infinity, this infinite union can be written as the sum of each individual probabilities. So this notation could be a little bit difficult to see, but if I just consider a finite union, which would be A union B, that would be the same as probability of A plus the probability of B, assuming that A intercept B is empty. So how do you see that? So here is the sample space. You have two events. Here is your event A, here is your event B. And since they are not overlapping, then when you apply this thing to here, you calculate the probability of this event A. Okay, and then here you calculate the probability of this event B. You add them up, that will give you the probability of just calculating the union of the two, which is A union B. This is something that we should expect to happen, okay, because they're not overlapping. When you calculate the probability, just be the sum of the two individual probabilities. Okay, so here is a diagram understanding this additivity. If A and B, they are disjoint, then the probability of A union B can be written as probability of A plus the probability of B. Okay, so you can write it in the following way. So now let us go through a few corollaries that can be derived from these axioms, with the hope that after going through these corollaries, we can gain more insights about why these axioms are so important. So first of all, we can show that the probability of A complement is just 1 minus the probability of A. Okay, so why is this true? Now, you can actually use the three axioms to show this result. Basically, you can look at the probability of A union A complement. Okay, A union A complement. Why are you considering that? But don't worry. At least I know that A and A complement, they are disjoint. They are not overlapping with each other. And so by axiom 3, okay, I can write it as probability of A plus the probability of A complement. Okay, and so now what is this? This is the probability of the sample space, and so this is equal to 1 by axiom number 2, and therefore I know that here I can have a probability of A complement. It will just be 1 minus the probability of A. Okay, so we have proved this result. How about the second corollary? If for any A which is a subset inside omega, this has to be less than equals to 1. Well, we know that this probability of A union of A complement, this is equal to probability of A plus the probability of A complement, and then we know this is 1, okay, and so now this is the complement, and this complement has to be bigger than 0 by the axiom of 1, and then you can see that if I remove anything here, okay, so PA will be equal to 1 minus P of A complement, and this is a number bigger than 0. Okay, and so if I remove that, then this of course it has to be less than equals to 1, and so we can show the second corollary. The third corollary says that the probability of the empty set is 0. This is true because the probability of the empty set union with the entire sample space, that is still the samples. That is the sample space. Okay, and then now the sample space will give you 1, and here this can be written as the probability of the empty set plus the probability of the sample space, and since this is 1, then you have probability of the empty set plus 1 will equal to 1, and so what is this number? This number has no choice, but it has to be 0. So we have proved the third corollary. Okay, so by going through these three corollaries, you can see that all the typical things that you would expect in the probability can all be derived from these axioms. How about this one? If A and B, they are overlapping, and then you want to calculate the union of A and B, you want to find the probability, that would just be A plus B minus whatever they are overlapping, which is the intersection of A and B. Okay, from this diagram, it should be pretty easy to show the results, but we can also do it more carefully in terms of proving the result. Okay, so how do we show that? We are looking at probability of A union probability of B. So what is it? Well, we can look at the diagram. The diagram says that I will have probability of A, but you don't want B, okay, plus the probability of A intercept B, and then plus the probability of B, but you don't want A. Now, notice that these three sets, this, and that, they are all disjoint because A, you don't want B, is this set, and then B without A is this set, and then A intercept B will be this set. So they are not overlapping, and therefore by axiom number 3, you can write them as individual sums. So this is true by 3. And then what? Well, what is A backslash B? Well, A backslash B is just A intercept B complement. Okay, and then we can have B intercept A, and then have probability of B intercept of A complement. Okay, how do we deal with this case? So let's do a trick here. Let us introduce another thing. Okay, so A intercept B, and here let us plus probability of B intercept C. Let's also add a probability of A intercept B, and then minus the probability of A intercept B. Okay, so these two you add and subtract, it doesn't really matter because they will cancel out each other. However, now you can group these two together and then these two together. What is the result of these two? If you go back to the diagram here, thus A intercept B complement is this term, and then B intercept A is this term. They are not overlapping, and therefore by axiom 3 again, I can combine them. I can have A intercept B complement, and then I can take the union of A intercept B. Okay, same for here. I can have probability of B intercept A complement, and then I can take the union of A intercept B. Okay, and then now I have the subtraction of A intercept B. So you can look at this is just the set operation between two unions, and then you can do some calculation, but you can also see from the diagram what is the union of this thing and then that thing. The union of these two will just give you the probability of A. And then here, this union will give you the probability of B. And then here you have minus the probability of A intercept B. So when you go all the way back, you can show this result. This is the union of A and B, where A and B are overlapping. You can calculate the probability using this formula. The next corollary that we want to show is what we call the union bound. This union bound says that for any events A and B, when you take the probability of A union B, it has to be less than or equals to the probability of A plus the probability of B. So why is this true? We know that probability of A union B is the probability of A plus the probability of B minus the probability of A intercept B. And since by axiom number 1, this is bigger than 0, and so this entire thing has to be less than or equals to A plus B without this subtraction. Okay, so then you can show that A union B is less than A plus B. The next corollary concerns about the if statement. If you have event A inside B, then you want to show that the probability of A is less than the probability of B. Now, why is this true? Well, you can draw a diagram where you have two sets. This is the set B, and then here is the set A. Then since A is contained inside B, then of course the probability of A would be less than the probability of B. So if you view it from the measure point of view, then you know that the probability is the size of the sets. And so if A is contained in B, then certainly the probability of A has to be less than the probability of B. So here is an example. If A is the interval from 0 to 5, B is the interval from 0 to 10, then of course the probability of A is less than the probability of B. So finally, let me show you some examples of how we can use the axioms to do some calculation. So suppose we have events A and B. Probability of A is X, probability of B is Y, and then the probability of A union B is Z. We want to find the probability of A intercept B. So this probability is what? Well, it is A union B, okay, A plus probability of B minus the probability of A union B. Now, why is this true? Let's recall the formula. The formula says that A union B is the probability of A plus the probability of B, and then minus the probability of A intercept B. Okay, so now you can move this to the left-hand side and then this to the right-hand side. Then you can have this result. Okay, so now you can plug the number in. Here you will get X, this you will get Y, and then here you will get Z. And so the probability of A intercept B is X plus Y minus Z. Okay, how about the probability of A complement intercept with B complement? Okay, so how do we calculate this result? Well, so you can see that this is A complement intercept B complement. That is the same as A union B complement. That's by the De Morgan's law. Okay, so if you have this probability of A complement intercept of B complement, that's the same as the probability of A union B, the entire thing complement, which is 1 minus the probability of A union B. So that will give you 1 minus Z. Okay, so now we can also try this example where you have probability of A complement union probability of B complement. So that is the probability of A intercept B complement. So that is 1 minus the probability of A intercept B. So you have 1 minus of whatever we have in A. So you have X plus Y minus Z. So that is the probability. And finally, we have this probability. So we have this probability of A intercept B complement. And so we can ask, well, how do we calculate this probability? So this is a little bit tricky. So we need to draw the diagram of A and B. So here is A, here is B. And now this A intercept B complement is this portion. Okay, and we know that this is basically just A backslash B. So how do we calculate this probability? Well, according to this diagram, we know that it is just the probability of A minus the probability of A intercept B. And so that will give you X minus the intersection of A and B. So that will give you X plus Y minus Z. So that will give you Z minus 1. All right, so I hope this example has given you enough idea of how to calculate the probabilities. If you have any question, please feel free to post on Piazza or send us an email. And I will encourage you to try our homework and to have some practice on calculating the probabilities. Thank you.